In section 7.3, we're going to come back and take a look at another way that we can simplify radicals. In fact, this is going to be probably the most important way that we simplify radicals. While the exponents in section 7.2 did allow us to do a little bit of simplifying, this type of simplification of radicals is going to allow us to take us to the next step of being able to add and subtract radicals together. The key to adding and subtracting is going to be that we're able to collect like terms, but we can't collect like terms until we have the radicals in the simplest possible form. And so our strategy in this section is going to be factoring out the perfect power. So if we're talking a square root, we're going to be factoring out perfect squares, cube roots, perfect cubes, and so forth. All right, so let's take a look at what we mean by the term perfect power. So we're going to begin by understanding what we mean by the phrase perfect power. So let's start with squares. What is a perfect square? When I say the term perfect square, well, those are the numbers that are squares of our counting numbers, natural numbers like 1, 2, 3, 4, 5, 6. The perfect squares would be 1, 4, 9, 16, 25, 36, and so on. It's the ones that you get when you square the counting numbers or the natural numbers. Now for variables, perfect squares are going to be ones that we get from squaring different powers of a variable. So if I took x to the first power and squared it, that's going to be x squared. If I took an x squared and squared it, that's x to the fourth. If I started with x cubed and squared it, I would get x to the sixth. If I did x cubed to the x to the fourth squared, that's x to the eighth, and you begin to see the pattern here, x to the 10th, x to the 12th. Notice even powers are what we get whenever we have perfect squares for variables. Now what about a perfect cube? Well, those are going to be the numbers that we get when we cube the natural numbers. Things like 1, right, because 1 cubed is 1. 2 cubed would be 8. 2 times 2 times 2. 3 cubed is 27. 4 cubed, 4 times 4 is 16. Times another 4 is 64. If you need to get your calculator up, by all means, there's no reason why you shouldn't do that. 5 times 5 times 5 is 125. 6 times 6 times 6 is 216. Okay? Now what about perfect cubes for variables? Well, that's going to be the case where you take an x to the first and see what you get when you cube it. Remember, power to a power is multiply, so it's x cubed. X to the second cubed would be x to the sixth. If you did x cubed cubed, that's x to the ninth. And you begin to see the pattern again. 3, 6, 9. What's the next one going to be? It's going to be 12, 15, and 18, and so on. So the powers are multiples of 3. Those are what we mean by perfect cubes. So let's talk about how we simplify radicals using the product rule for radicals together with this concept of the perfect power. The product rule for radicals says that the square root of a, b, whenever we have non-negative real numbers a and b, that's a is 0 or larger, b is 0 or larger, and they're both real, that we can get the same thing as the square root of a times the square root of b. That is, if we have something inside like 20, 20 is the same thing as, say, I don't know, 2 times 10, right? Square root of 2 times 10. Well, by the product rule, you can do is the square root of 2 times the square root of 10. 20 is also, say, square root of 4 times 5. 20 is 4 times 5. So that's the square root of 4 times the square root of 5. Less interesting, but still true. 20 times 1, right? Square root of 20 times the square root of 1. Now look at the middle one right here in particular. This one right here. Now what's interesting about that? Well, look at the answer. Right here is one I can evaluate, right? That becomes 2 times the square root of 5. Now the other two, there's nothing I can do on those to further simplify, but now I've got one that actually simplifies further. Okay? I've actually pulled out a factor from the inside. That's the kind of simplifying we're going to be doing. Now what about x to the 7th? Now x to the 7th could be written as, I'll say, x to the 4th times x cubed. So you could put a square root over each one of those. X to the 7th could also be x to the 2nd, x to the 5th. Square root over each of those. And it could be x to the 6th and x to the 1st. Right? Square root of both of those. Now in this case, it's the last one that I've written that is interesting to me, because on that one, I simplify it further. In fact, I can simplify all three of these further, but this one, I've pulled out as many possible x's as I can and still be able to simplify. So x, square root of x to the 6 is x cubed, because that's the number that that's the variable expression that when squared gives me x to the 6th times the square root of x. Notice I can't pull any more x's out because I only have x to the 1st. I've made the inside of the radical as simple as possible by pulling out something that I can take the square root of, by factoring out something I can take the square root of. So combine the idea with numbers and variables together, and we now have a technique for simplifying radicals. That is, making the radicand as simple as possible by pulling out any perfect powers that are factors of that radicand. So here's our general strategy. To simplify radicals using the product rule, we'll do the following. If the radicand contains a coefficient other than 1, right? If it's 1, there's nothing really to be done. But if it contains a coefficient larger than 1 or some other number the size 1, we're going to write it as the product of two numbers, just like we split the 20 up on the previous page, one of which is the largest perfect power for that particular index, meaning that if it's a perfect square, perfect cubed, whatever index you have on the radical. So you pull out the largest possible perfect power of that number, write it times whatever's left over, right? You're also going to do that with each variable factor. So if you have x's, y's, z's, those sorts of things. It's hard to write E when you're saying Y. I apologize. So write each factor as the product of two factors. Write each variable as the product of two factors, one of which is the largest perfect power of the variable for that given index. Then we use the product rule to write the radical expression as a product of radicals. What we're going to do is we're going to split it up just like we did on the previous page and put the perfect powers under one radical and all the leftovers, the things that I can't pull any other perfect powers out of, underneath the other radical. Okay? Place all the perfect powers under the same radical. The reason you do that is the one with all the perfect powers in there, they all have nice round whole roots coming out of them. You can actually take that radical and simplify it completely out. So simplify the radical containing the perfect powers, and you're done. Alright, so take for example this 75 right here. Now 75, we're thinking, okay, 75, how can we split up 75 as the product of two numbers, right? 75 is 5 times 15, but that doesn't help. What about 25 times 3? One way to think of this is to just go through your list of perfect squares and find the biggest one, in this case 25, that divides into your number. Okay, so 75 is 25 times 3, so put a square root over each one. But you can take the square root of 25, that's 5, with 3 left inside the radical. All I'm doing is actually taking the square root, leaving the times in between there, so 5 times the square root of 3. For the cube root of 108, we're looking for perfect cubes. So just refresh your memory. What are the perfect cubes? That's, not cubs, cubes. Cubes are far from perfect. All right, perfect cubes would be 1, 8, 27, 64, 125, all of a sudden we're beyond where we're going to be able to split 108. Now, do any of these divide into 108 nicely? Of course, one does, but that doesn't interest me, right? We want to actually split this up into something smaller times something else. So 8 does not go into 108. If I plug it in my calculator, I get a decimal number, so it doesn't go in evenly. But 27 actually does, right? That's the sound of my calculator hitting the table. How about 108 divided by 27 is 4. So this is the same thing as 27 times 4. Again, remember, the reason that I'm using perfect cubes is because we're talking cube roots here. So cube root of 27 times the cube root of 4 is 3 cube roots of 4. Okay. What about these radical expressions? Now these you can actually simplify almost immediately. What's the square root of x to the 4th? Right? That is x squared. Now you can think of this two ways. It's true because x squared squared is x to the 4th, or just remember the rule for dividing exponents. That is, if you have a root and a power, the power is the numerator, the root is the denominator, and you can write down the answer immediately. What about this one? I like this technique, the second technique I have here, because we can get the answer almost immediately without having to try to guess what it has to be. What is x to the 12th? Take the cube root. That's 12 divided by 3, so x to the 4th. On C, we have the 5th root of z to the 35th, so that's going to be z to the 7th, because 35 divided by 5 is 7. Okay? So we'll use this idea as we start to simplify it. We're looking again, perfect powers are those ones that evenly divide by the root. Okay, let's look at some where the power inside is not necessarily a multiple of the root. All right, let's simplify the radical expression. Now what we're trying to do is find the largest perfect power that goes into y to the 11th. Now remember, perfect squares for variables means that the power is a multiple of the index. We're talking 2 roots, so we're going to have an even root. We need to find the largest even power less than or equal to 11. Right? So what's the largest even number less than or equal to 11? Well, it's 10, right? So I'm going to write y to the 11th as y to the 10th times y to the 1st. Leave the root on there. And now I can take the root of y to the 10th, which is y to the 5th, times the square root of y. Okay, you just leave the leftovers in the other radical. Okay, what about r to the 43rd? Now we've got 43, we've got 6. What is the largest multiple of 6 that's less than or equal to 43? 6, 12, 18, 24, 30, 36, 42. Right? So I can write this as r to the 42 times r to the 1st. Take the 6th root of each of these, and you'll have r to the 7th, 42 divided by 6 is 7, times the 6th root of r. Okay. Now, what if we have multiple factors in there? We just got to repeat this for every factor that we see. X's and Y's, numbers, X's, Y's, and Z's like we have down here. Let's just do this process one by one with each factor, okay? So let's start with the X. Okay, and I'm going to put the perfect powers here, and I'm going to put the leftovers right there. Okay, perfect powers and leftovers. So x to the 14th. Now, what's the largest multiple of 2? Right, because no index means 2 index. Less than or equal to 14. Well, it's perfect already, so I'm going to put all of it, x to the 14th, over here. What about 21? I need the largest multiple of 2, so the largest even number that's less than or equal to 21. So that's going to be 20, right? So I have y to the 20th over here with the leftover of y to the 1st. So put all of these under one radical and this under the other radical. Now take the square root of the perfect powers. X to the 14th is x to the 7th. Y to the 20th is y to the 10, square root of it that is, times the square root of y. All right. All right, now we're looking at fourth roots. So we got x to the ninth. Here's my perfect powers. Here's my leftovers. So multiples of 4 less than or equal to 9. 4, 8, right? So it's going to be 8. X to the 8th. And how many are left over? We have 1 left over, x to the 1st. What about 27? Multiples of 4. See, 28 is, but that's too big. How about 24? Y to the 24th. And how many more do I need to get to 27? I need 3 of them, right? So I have 3 left over. So put the fourth root over this one. Make sure you use the same radical as is in the problem. Fourth root of x to the 8th is x squared. You're dividing the power by the root. 8 divided by 4 is 2. Y to the 6th times the fourth root of xy cubed. And that's it. Now let's do one last one. Here's a square root. So we're going to put our perfect powers here, leftovers here. Now what does 50 split into? What is the largest perfect square? Perfect squares being 1, 4, 9, 16, 25, 36. I think past that I can't get anything divided into 50, so 25 goes in there. So 25 here and a 2 here, because 25 times 2 is 50. Remember, with the exponents, you're adding to get to the number inside. But when the number's down here on the base, you're talking multiplication, because that's the operation that's in between each of these factors. All right. X to the 7th means x to the 6th with 1 left over. Y to the 14th is already perfect, so we'll leave it all in here. And z to the 4th with 1 left over. Square root over each one. We will have 5. Because the square root of 25 is 5. Square root of x to the 6th is x to the 3rd. Square root of y to the 14th is y to the 7th. And square root of z to the 4th is z squared. That's the square root, still 2xz. And there's your final answer. Alright, that's the end of this section, section 7.3. You now know how to simplify radicals by pulling out perfect powers. We'll use this now in the next section as we start to add and subtract these radical expressions together.